In the second part of section 41, we will continue to look at piecewise function modeling. The use of the calculator is required for this section. When we talk about the total area under a curve, we're taking the absolute value of the area from curve to the x-axis. So what may help is to draw a line on your paper along the x-axis from the first time you have a point, so at -2 in this case, all the way up until we get to +2. And then we're going to be finding the area of this triangle here, of this triangle in the middle, and then finally of this triangle right here. So as our lines connect to the x-axis. Now, when we actually calculate this, you've got to remember, if we're dealing with a triangle here, we're going to be doing 1/2 base times height. So if it's underneath, and you can see these ones in red, we're going to consider these to be in the negative region. So that's why those parts are going to have negatives for the 1/2 part. So it's -1/2, and then it's the base. So the base would be 1 unit, and then the height is 1, 2, 3 units, and that's where the 1 and 3 are coming from here. Now, because we're going to be taking the absolute value here, this is going to end up being a positive result. The middle one, we're going to again do 1/2. This time the base goes 1, 2 units, and then the height here is 1, 2, 3 units. And then we'll calculate that, which is going to be positive inside, and its result is going to also be positive. And then finally, for our last region, again, we've got the negative because it's underneath the x-axis. And then it's 1/2, the base is 1, the height is 3, and we'll calculate that. And so when you do calculate that, we're going to get, in this case, we would get the absolute value of -3/2, which is +3/2. This right here is going to give us 3. And then this right here is going to give us -3/2, and the opposite of that is +3/2. So this is really like 1.5 and 1.5, which is 3. And then here's another 3 in the middle, and that's where that 6 is coming from. But when we talk about net area under the curve, this is when we're actually not going to take the absolute value. We're going to actually consider its signs. So if it's underneath, it's a negative. If it's above, it's a positive. And if it's, again, that last piece is underneath, so that part will be negative as well. So it's the exact same thing, but we're not taking the absolute values. And this time, as we talked about before, this part is going to be 3. These two parts sum to -3. So that means that it's all canceling out and giving us 0. So the total area under the curve, 6 in this case, the net area would be 0. So you're going to be doing the same thing with this one eventually, but the first question says, find the slope of the piece which contains x equals -2. So since it's x equals, we go to the x-axis at -2, and that lands us on this piece right here. So we need to find the slope of this piece. And so what I would suggest is that you look at it from end point to end point. And this one looks like it's going down 1, 2, 3 to go over 1, 2, 3. Now -3 divided by 3 is -1. And if you check that, it does look like it's going down 1 and over 1, down 1 and over 1, down 1 and over 1. So that would be our first slope. The next question says to find the slope of the piece that contains 0. So pause the video and go ahead and try that on your own, and then play it through to check your answer. Now 0 is here, and again, that's on this piece right here. So I'd suggest that you look at this from endpoint to endpoint, and if I'm looking at, again, rise over run, so it goes up 1, 2, 3, 4 units to go over 2. 4 divided by 2 is going to give you 2. And then for question number 3, again, it would be a good idea to pause the video, but at 2, this is going to be a slope that goes down. It's going negative. So we're going to go down 1, 2, 3, 4 to go over 2. -4 over 2 gives us -2. Now for our next question, this is total area under the curve. So again, I'd suggest that you start, the first time we have a point here is at -4. So I would make a line along the x-axis spanning from -4 all the way over to 3. And then what we're going to do is drop a line straight down at 3. So that would be like right here. And then we'll drop a line straight down at -4 to kind of make these different regions. And when we're coming up with the total area, you're going to be finding the area of each piece. Again, you want to think about whether they'd be positive or negative, but with total area, we're going to end up taking the absolute value, so everything will be positive anyway. So with that first piece, it's going to be 1/2. The base is 1. And the height is also 1. Our next region is going to be in the negative region. So when we're doing this one, it's going to be 1/2. The base here looks like it's 1, 2, 3 units. And then our height, you got to make sure you're looking at that at the highest point, which would be here. So that's 1, 2 units. Our next region is in the positive region, so we're going to have a positive result there. This one it's 1/2, the base is 2 units, the height is also 2 units. And then for that final region, it's going to be -1/2, and then our base is 1 and our height is 2. So as we calculate each of these regions, this is going to be 1/2. This right here, I'm going to cancel these 2's. This would be -3/2, but then taking the absolute value makes it positive. This right here is going to be, we'll cancel a set of 2's. So this set is going to be a +2. And then our last set, if I cancel those 2's, I'm going to get a -1 here. So that section is going to be 13/2 or 6.5. And then for number 5, when I'm looking at the same thing, but I don't have any absolute values anymore, so this time when you combine everything, we end up with -3/2. Now for number 6, the slope of the piece that contains 4. So I go to 4, that puts me on this piece right here. And for this piece, I am gonna go down 1, 2, 3 units to go over 1, 2, 3 units. So it's -3 divided by 3, so that's gonna be -1. For number 7, this one is the total area under the curve, and you want to be careful here. So again, first point is at -5, last point is at +5. I'm going to go ahead and make a straight line going along the x-axis all the way through. And then from here, I end up with a half of a circle here. So instead of doing 1/2 base times height, like we did for the triangle, this time I'm going to have to do 1/2 pi r squared, because the area of a circle would be pi r squared, and we need to take half of that. So 1/2 times pi. Now, how do I figure out the radius? The radius is the distance from the center to any point on the outside of the circle. Now, you wouldn't want to go on diagonal here. We want to look along the grid marks. So this would be 1 unit, or this would be 1 unit, or this would be 1 unit. So any way we look at it, it's 1 unit, and that's where we're calculating that. Now, from there, we'd be looking at this next piece, which again is a half of a circle. It's underneath, so I've got a negative attached to it. And then for this one, when I do 1/2 pi r squared, the total diameter here, the distance all the way across, is 1, 2, 3, 4 units, which means that the radius is right here, and that's 2 units this way, it's 2 units this way, and it's 2 units this way. And that's why our radius is going to be 2. Then with this next part, the base is going to be 1, 2, 3 units. The height is 2 units. And then for our last region, again, this is a triangle. Base is 1, height is 1, and so that would be calculated there. Again, making sure the parts that are underneath would have the negatives attached to them, although we know with total area that those are going to turn positive anyway. What we should end up with for this one is either 5 pi over 2 plus 7/2, or you could write it as 5 pi plus 7 all over 2, because again, you can't combine the 5 pi in this case with the 7. And then when we look at net area, again, that's going to be the exact same setup, just removing all of the absolute values. And when we do that, it should combine to either give us -3 pi over 2 plus 5/2, or you could put -3 pi plus 5 all over 2. Okay, this next one's a little bit trickier when we get to the total and the net area, so we'll kind of do this one together. At -2, when I'm looking at the slope of this line, this one goes down 1 to go over 1, 2, 3 units. So this one's going to be -1/3. For 10, when it says to find the net area under the curve, again, I want you to take that line from -5 all the way up to 4 and just go ahead and connect that all the way through. Now from there, the first part is a triangle, so I'm going to do, and again, this one is asking net area, so we don't have absolute values in this case. So this is -1/2, the base is 1, the height is 2. Now when you get to this next region, we don't have an exact formula to be able to have done like this entire thing at the same time, this entire region. So we're going to break this up into a few different chunks. The first one is going to be looking at this triangle. And again, it's above, so I'm going to keep that positive. It's 1/2, the base is 1 unit, the height is 2 units. And then for the next region, I'm going to think of this as a triangle. And then for this next region, the way that it's typed in here, we'll talk about the way that this expression is written, but to be honest, I probably would not write it this way. I would break this up into two separate pieces. We can see that here. For the rectangle, I would be doing base, which is 3, times the height, which is 1. So that alone is just going to be 3. And then for this piece up here, I would be doing 1/2, the base is 3, and then the height is just 1 unit. So I would have half of 3 times 1, so that's just going to be 3/2. So you can do it either way, but again, my recommendation would be to actually split those up as two different expressions. Now this next part is the trickier part. Right here, to figure out this space and then this space right here, what we're going to want to think about is actually finding the area of a rectangle and then finding the area of this half a circle right here. If you get the area of the rectangle and then you subtract out the half of circle, then the pieces that you're left with would be here and here, and that's what we need to calculate. So the area of that rectangle would be base times height, so 2 times 1. Then I'd have to subtract out the area of this half a circle, which would be 1/2 pi r squared. So 1/2 pi, the radius here is just 1. So at this point, we really have 2 minus 1/2 pi. And then for our last two pieces, one of them is 1/2. It's base times the height, which is going to be 1/2, 1 times 1. And then our last piece is going to be 1/2 times 1 times 1. But again, that one has a negative because this is net area and it's underneath. So now when we go ahead and combine everything in this problem, what you should end up with is 13/2 minus pi halves, or 13 minus pi all over 2. Okay, and then for this one, the slope of the line that contains 1, so we're going to go to 1. It's this piece right here. To get the slope of this, I'm going to go endpoint to endpoint. We go up 4 to go over 2, so that slope is 2. For the next piece, when we're looking at 3, that's going to put us on this piece. I will say that this looks a little bit crooked, but this part should be a straight line right here going from here to here as the endpoint. So this looks like it goes down 1, 2, 3, 4. So it's -4 divided by 2, and that's going to give us -2. And then for 13 at 6, we're on this piece right here. It goes up 1, 2 to go over 2, and that's going to give us a slope of 1. And then when we talk about total area under the curve, this is when we do have absolute values. So again, I would make a line starting here and ending at 7. Straight along the x-axis, and then we're going to have to connect this right here to form our last region. First region is a triangle, so 1/2 base times height. I've got 1/2 4 times 4. Next region, also a triangle. It's in the negative region, so I'm going to keep that negative inside the absolute value, and it's 1/2. The base there is 2, the height is 1. And then that final triangle is 1/2 base times height again, so 1/2 1 times 1. Put that all together, everything becomes positive, and it's 19 halves for that one, or you could have 9.5. And then for 15, when it's the net area, it's all the same numbers, but everything ends up, it doesn't switch signs. So this is going to be positive, this will be negative, this will be positive. And when we put all that together, it should be 15 halves or 7.5. So now we kind of switch topics a little bit, but we do need that previous information to be able to answer the questions associated with this part. So this is kind of a chart to help us to realize what we're looking for, whether we're going to be looking at the area under the curve or if we're going to be looking at the slope. So say it's a position versus time graph, and they're asking you about the velocity. If you're moving down this list, you're going to be looking at the slope of the line. If you're moving up the list, say it's an acceleration graph, and they're asking you a question about velocity, or it's a velocity graph and they're asking you a question about position. You're moving up, you're going to be looking at the area under the curve. So here's some examples. It says that the slope of the position is the velocity. And again, it's because you're moving from here to here. Going down the curve is when we're looking at slope. And then it continues to provide other examples. You can see the ones in red are as we're moving down the chart. The ones in blue are as we're moving up the chart. And so now we're going to review a couple problems and we're going to answer some questions. So 16 says to find the velocity at 1. So again, this one is a position versus time graph. So if I go really quickly back to this graph, it's a position versus time. I'm looking for velocity. So since I'm moving down, that is going to tell me to look at the slope. So I go to 1 and I need to find the slope of this piece. And this is going to go up. it looks like to get from here to here, it goes up 4 units to go over 2, so it's 2. And for 17, if we're at 3, and again, we're talking about velocity from a position versus time graph, this one looks like it's going to be negative. It goes down 1, 2, 3, 4 to go over 2. So that's going to give us -2. At 6, when we're looking at this, we're going up 2 to go over 2, and that's going to give us 1. And then now we're looking at a velocity versus time graph. So again, we're moving down the chart. If I were to go back through my different slides here, you would see, again, that we're going down. So that's going to tell us to go with the slope. So again, if I go to 1, it's here. I would go up 1, 2, 3, 4 over 2. The answer is 2. The acceleration at 3, I'd go to 3. That puts me on this piece, and we know that the slope of that piece is going to be -2. At 6, same thing, we're looking at the slope there, and that's going to be 1. Now for 22, it says to find the total distance traveled from 0 to 7. So again, we're looking at a velocity graph, and we're trying to find the total distance, which is like a position. And it says from 0 to 7, so I'm going to start here at 0 and end here at 7, and that's when I'm going to actually want to calculate the area under the curve. So my first area is going to be 1/2, the base is 4, the height is 4. My next area is another triangle, so again, that's going to be underneath, and this is talking about total distance, so it's absolute values this time. 1/2, and then base is 2. So in this case, it's going to be negative, and then the base is 2 and the height is 1. And then for my final piece, it's 1/2, the base is 1, the height is also 1, and we'll calculate as such, and that should give us 19/2. And then for 23, if they're looking for the net distance, and again, we've done this problem previously, it was just presented in a different way. This one, when I get rid of the absolute values, is going to be 15/2. Okay, so for our next one, this one says it's an acceleration versus time graph. So we're going to be moving up to velocity. So if it's saying find the total velocity from 0 to 7, again, that's telling us with absolute values to calculate those different areas. And once again, we've already used these exact same numbers. It gives you 19/2. Then when we're asking about net velocity in that same exact setup, again, net is when I drop those absolute value signs, and combining those is going to give us 15/2. So it really depends on what type of graph. That's going to determine what answers we're going to get, or like what process we're going to use. So for 26, a car is traveling on a straight road for between 0 and 24 seconds. The car's velocity, v of t, in meters per second is modeled by the piecewise linear function defined by the graph below. For part A, find the area under the curve. Using correct units, explain the meaning of this area. So when we go to look at this one, it's important that we consider this is a velocity versus time graph. And so again, if you think about that chart, if we're moving from velocity and we're asking about the area under the curve, we're going up the chart, and that tells me that it goes to position, which position is going to mean like distance in this case. So in this case, we're finding the area of a trapezoid. So it's going to be 1/2. The height is 20, and then we've got to find the sum of the bottom and the top of the trapezoid. So this bottom piece is 24 units, the top piece is 12 units. Together, that gives you 360. So this means that the car travels 360 meters in 24 seconds. For B, find your acceleration at t equals 12. So again, this is a velocity graph, and we're looking at acceleration. That causes us to travel down the chart, and traveling down the chart is going to tell us to look at slope. So I want to go to 12, and that puts us here. Now the slope of this piece right here, it doesn't go up at all. So that's 0 over 12. And so that's just going to be 0. So that means that the car is traveling at 0 meters per square second. So that means that the car is accelerating at 0 meters per square second. For C, find your acceleration at 20. So we're going to use the same process and find the slope. So this one, the slope of that piece is going to be, it's going down a total of 20 to go over a total of 8. And so when we simplify that, you're going to either get 5/2, -5/2, or -2.5. And again, that's meters per square second. So for this one, you want to be kind of careful. We're looking at the average acceleration over the interval just from 8 to 20. And again, because this is velocity and we're talking about acceleration, we're moving down the chart. So that's going to tell us to find the slope. Now, essentially, we need to find the slope between these 2 points. And so you really could try to count this. And I would say since they both land at nice grid marks, you really could say it goes down 5, 10 to go over 4, 8, 12. And so you could simplify from there. Or what you could do is actually plugging it into a formula. And you would think about the ordered pairs here. This ordered pair would be at like 8, 20, and then this ordered pair over here is at 20, 10. So when we do this, you would want to subtract the y's on the top and subtract the x's in the denominator. And so that is set up for you right there, which again gives us that same result of -5, 6. Again, I think it's easiest if they fall at nice grid marks to just go ahead and count that like I did the first time. But if they didn't fall on nice grid marks, then we may need to actually calculate it with that the slope formula right here. And then for this one, it says we're trying to explain like what our answer means. So since we got -5, 6, we're going to get -5, 6. And this is the car's average acceleration from 8 to 20. And we want to make sure with acceleration, we're using meters per square second. This one is talking about the acceleration of the bicycle at 7.5 minutes. So again, we want to look at what kind of graph it is. It's a velocity. So moving from velocity, asking about acceleration is going down the chart. So that's going to tell us to look at the slope. So I've got to go to 7.5, and that's going to put me on this piece right here. And it's important that we're paying attention to the units right here because going down 1 grid mark here is actually going down 0.1, and then we're going over 1. So this is going to give us -0.1, and that's miles per square minute. Again, being careful that we're paying attention to like the units that we have here. So for part B, Karen forgot her homework and had to return home to get it. At what time T did she arrive back home? So if you're looking at this graph and kind of trying to interpret what this means, this is a velocity versus time graph. So as she's kind of stationary in one spot at home, that's going to have to be at 4. So when we're looking at that, since this is just in minutes here, we're going to say that she got home at T equals 4 minutes. For C, how long was Karen home when she got her homework? And again, we want to indicate this in units. Well, it looks again like she's stationary in that same place or traveling, not traveling any distances. Her velocity is 0 right here, and that's for a total of 1 minute. For D, what is Karen's average acceleration from 6 to 12? So if I'm looking from 6 to 12, and again, this is velocity and we're looking at acceleration, so moving down the chart is going to tell us we care about slope. So we want to find those 2 pieces and then calculate the slope between them. And again, like I said on the previous problem, it might be a good idea to just kind of count this. So this one would go down 0.3 to go over. We end up at 12, but it's only 6 units away from 6. So it's -0.3 divided by 6. And so that should give us -0.05, and that's miles per square minute. E, how many miles is it from Karen's home to school? So with this one, again, if it's a velocity and I'm talking about position or distance, I'm moving up the chart. And when we're moving up the chart, that's when we want to look at the net areas. We can start here when we know she left her house the second time to get to school at 12. So when we're starting here and going through and calculating these different pieces, you can do this a few different ways, but this is how I have this one broken down. We've got this triangle, then we've got a rectangle, we've got this small triangle right here, we've got a big rectangle right here, and then a small triangle. Putting all that together gives us a total of 1.4 miles, and that would be the distance from Karen's home to school. We have another problem here. Nate is walking around town during his holiday shopping. He began his walk 4 miles from his home at 7 a.m. when the store is open. Nate's position, distance from home, is modeled by the piecewise linear function below. So again, if I'm looking at position versus time, and now they're asking about velocity. So if I'm moving from position down to a velocity, I care about the slope. So if this is at 7 a.m., to figure out 8 a.m., that would have to be 1 unit over. So we're going to be right here, and I want to figure out the slope of this part. So it's going to go up 1, 2, 3, 4 to go over 2, and that means it's 2, and then it's in miles per hour. For B, Nate stops at home when his arms are full of packages. At what time does Nate stop home? Include AM or PM in your answer. So Nate is going to be at home in this at this point right here, because again, this is his position, and it says that he began his walk 4 miles from home. So if this is home, that -4 would be 4 units away. And so then when we hit that 0 again, that's going to account for him being at home. And so since this is considered 7 a.m., this would be 8 a.m., so 9 a.m. is when he stopped home. He also stopped home at 12 p.m. because that's where it's again hitting that. And then also for C, find the average velocity during Nate's walk. So if we're moving from position to velocity, again, we care about slope. And so if we're looking at average, we want to look at the endpoints. And from here, calculate that. So again, you could do this with the formula here, or I can just count this. It looks like it goes up 5 to go over 10. So that is going to give us 1/2 miles per hour. For D, Nate's velocity is negative between what times? And so when we're looking at that part, we're looking at where is the slope negative. And there's only one time that the slope is negative right here, and that is between this point and this point. So again, if this is 7 a.m., this is 8, 9, 10, 11 a.m., and then this would be 12 p.m., 1 p.m., 2 p.m. So it's between 11 a.m. and 2 p.m. So that completes our lesson for section 41, part 2. So please complete the homework assignment in the practice set that you have.